Can I get a worksheet 5?
Yeah, does anybody not, would anybody benefit from a hard copy of worksheet 5?
Yeah.
Would you mind distributing those?
Sure.
Thanks. What was, and now, oh yeah, you've been recording? Great. What was the lab that we did last time?
Mass versus.
What was the lab that we did last time? Nick?
It was like force.
Michael?
As a function of mass.
Yeah, so I guess we,
He was distracting force. No, I was about to say it.
Or
All right.
acceleration.
no, so we had done last week a biggish lab that had to do with acceleration and force and mass. But the one that we did last time, tune in, had to do with hanging different amounts of mass from the spring scale and finding out what the gravitational force on each mass was. So if this is the spring scale, here's the hook. We would hang a mass m there, and there would be a gravitational force down and a force, I guess, by the scale on the mass up. And if I held it at rest, I would know that this upward force balances that downward force because there'd be no
Movement. Vertical acceleration.
acceleration. Yeah, right. Are these even different?
Yes. Yes. Yes.
They are different. Could someone, I guess, let me make a contrast. 1 meter is about 3.2 feet. Is 1 meter different than 3.2 feet? I'm going to say no. It's the same thing. I guess plus or minus like the decimal approximation. But like this is a meter. This is 3.2 feet. It's the same thing. Are these really just like the same thing expressed differently? They're not. Could anybody convince me that that's the case? No?
Mass, just like the amount of stuff something is like made out of.
Mm-hmm.
Cumulative weight of its atoms. And is just basically how much you weigh with the addition of gravity.
Yeah, I like that. This is how much stuff is in something, and this is like with the addition of gravity, like what the gravitational force is.
Mass doesn't vary, but your weight, I guess if you say you weigh 30 pounds, or someone weighs 30 pounds, and like on the moon, you weigh less than change.
Okay, that's a really clear example. If I went to the moon, then this quantity wouldn't change, my mass, but this quantity would change. By the way, a synonym for gravitational force, weight. We had talked about this last time. I wish that I didn't have to do this. I wish that I didn't have to like say, oh yeah, weight is not mass, because then every time we talk about weight for the first few times that you practice it, you're going to have to remind yourself that it's not the same as mass, even though outside this room people do use those terms interchangeably. I need to use the word weight precisely, and because mass is not the same thing as gravitational force, I need to choose which of them to use the word weight to mean. And this is the choice. The definition of the word weight in this classroom is gravitational force. So the unit of weight is newtons. You could measure it in pounds. It turns out that 1 pound is about 4.4 newtons, just in the way that 1 meter is about 3.2 feet. They really are the same thing.
Can I ask a question about the Newton's unit?
Sure.
Can you like write it on the board, any kg, meter?
Yeah, and you know what I'll actually do? Let me write this instead. So the question is about the units of newtons. And here's why I started with this equation. You wanted to talk about units, and I wrote Newton's second law, and the reason is so that I can say, what's the unit on the left-hand side there?
Meter per second squared.
Yes. And what's the unit in the numerator here?
Kilogram per.
Let's say it's newtons, but I don't disagree. And what's the unit of mass down here? Kilograms. We'll measure mass in kilograms rather than grams so that we have sort of a human scale mass. Okay, and so if you don't remember what a newton is in terms of kilograms, meters, and seconds, here's how you remind yourself. you multiply through by kilograms and say that a kilogram meter per second squared is a newton.
Okay, so it's, it's like if you have 3 newtons, does that mean you have 3 kilograms per meter per second squared?
I'd say kilogram times meter
Yeah,
per
sorry,
second.
3
Yeah.
kilograms times.
Yes.
So is the 3 kilograms, is that the mass of, like,
Yeah.
what is the mass of?
Yeah. So I'll answer your question, but I'll also say that maybe every time you hear about 3 newtons, I might encourage you that you don't need to think about drawing it physically back to this example, but I will show you that I can render a physical explanation of that. 3 kilogram meters per second squared is the amount of force that you would have to apply to a mass of 3 kilograms to give it an acceleration of 1 meter per second squared.
Sorry, say that one more time?
Yeah. 3 newtons is the amount of force that you would need to apply to a 3 kilogram mass to give that mass an acceleration of 1 meter per second squared.
Okay.
Yep. Or to give a 1 kilogram mass an acceleration of 3 meters per second squared.
That's
Right.
cool. Okay.
Yeah, it's cool. Okay, so did anyone, I think there were some groups that were able to get some data and graph it. Either over the weekend, you maybe did this number 1, or before you left the room on Friday. What was the result? James?
It was super linear.
It was pretty linear. And so, did anyone else have a result? Was that your result? Did anyone get a different result?
Oh, we got that too.
You get an r squared.
We did it like segments of 50 grams.
Mhm.
Just went up by the exact same amount each time.
Yeah. Is 0, 0 a point on this graph?
Mm-hmm.
Yeah. Can I ask, like, what? So I guess if it's linear and we think 0, 0 is a point on the graph, I guess the vertical thing isn't really y. It's what? Newtons is the unit, but what is the quantity on the vertical axis? Yeah, it's gravitational force. And that's equal to, let's see, what slope did you get? Does anyone have a value for the slope that you had?
I think they're like 10.
If we were to do this data, then I think you're right, Harry. You had said about a slope of 10.
Yeah, I think 10.
That is true. And at 10, and what's the unit of that slope?
Fg over m.
I guess it would be the units of the vertical divided by the units of the horizontal. What are the units of the vertical?
Newtons over.
Newtons per kilogram. And what's the thing on the horizontal axis? What's the quantity? Mass. Okay. So we had said that a meter per second was a velocity appropriate for a situation where for each second of travel, there is 1 meter of displacement. We had said that per means what? For each or for every. So what is a slope of 10 newtons per kilogram? Rob?
For every kilogram, there's 10 newtons.
Yeah. For every kilogram of mass, there are 10 newtons of gravitational force. So if I have, like, this is about a kilogram, this experiences about 10 newtons of gravitational force. So it's falling off. If I had 2 kilograms, there would be about what gravitational force? About 20 newtons. Yeah. Okay. That's this lab's result. The test on this unit will be a week from this coming Wednesday. I don't know if I've clarified very much for this class. If you have 3 tests scheduled in the same day, do you know?
Email me.
Well, yes, do email me. But do you know that in general in school, if you have 3 tests on the same day, and I don't think anyone does for this class next Wednesday, but if you were to, you know that you get to reschedule one of them, such that you don't.
The last test.
So I guess that's true. I think it is technically like you can reschedule the last test that was scheduled. But for this class, if you have 3 tests and this is one of them, we can reschedule this one if that's your preference. So whether or not I was the last person to schedule the test, if you want this to be your one of 3 to move, then that's fine with me. I don't need to investigate when the others were scheduled. So we have our test, and I'll collect a homework packet next Wednesday. We're getting towards the end of our new material. Nick?
So do we include this, like should we do this and include it in our homework package?
I will not collect that as part of the homework packet. A mass m on the surface of the Earth feels a gravitational force mg. That's this law. That's the result of this lab. So m, and then I'm going to call this green thing g. And if we were really careful, we would have found that the slope was about 9.8 newtons per kilogram. Does that ring a bell?
Yes.
It does. Let's talk about that in a little bit. Yeah, we've met lowercase g to mean 9.8 what before? Meters per second squared. That was the acceleration due to gravity. And we're going to talk about that in the next slide. But for right now, here's our gravitation force law. That on Earth's surface, there's a gravitational field strength of 9.8, about 10, feel free to use 10, newtons per kilogram. For each kilogram of mass, an object experiences about 10 newtons of gravitational force. So on the moon, it's like 3 point something newtons per kilogram of gravitational force. There's a different value of g there. Weight is gravitational force. It's not the same as mass. If I go to the moon, Noel, you already told me this. Which of these changes when I go to the moon? My weight does. My mass doesn't change because the amount of stuff in me doesn't change. So we welcome this new math model to our class. Gravitational force on an object is its mass times g. And here, our lab shows that g has a value of about 9.8 newtons per kilogram. I've said here m is the gravitational mass. What I'm saying is that like the m in this equation kind of tells you about how hard Earth's gravitational force pulls on it, right? This has a large gravitational mass because like Earth exerts a pretty large weight on it, exerts a pretty large gravitational force on it. The gravitational mass is a feature of an object that tells you about how strongly that object experiences a gravitational force. This object has less gravitational mass because Earth has less of a tendency to exert a large gravitational force on this mass. Rob?
So G is 9.8 newtons per kilogram because newtons per kilogram is equal to meters per second.
I would.
Didn't we just prove that?
So we did, actually. When Harry brought up the units, I did say that a newton per kilogram was the same as a meter per second squared. So this 10 newtons per kilogram is 10 meters per second squared. And I'm going to link them more seriously on the next slide. But does everybody see that? This 9.8 is not just a coincidence. 9.8 meters per second squared is 9.8 newtons per kilogram. So what's up with that? And I'll tell you what's up with that. But you used the word because, though, I think, Rob. I'm not sure I would say that G is equal to 10 newtons per kilogram because that's equal to 10 meters per second squared. The way that we got this newtons per kilogram was looking at this lab and seeing that the units of the slope were the units of the vertical, newtons, divided by the units of the horizontal. So if I say, why does this have units of newtons per kilogram? I'll say because that was the lab that we did. We had mass as an independent variable and gravitational force as a dependent.
G. G1.
Let's, oh yes, comma, yeah. Weight is Fg, not the same as mass. Okay. It's anticlimactic. Here's a physics problem. I take a mass, m, and I drop it. Let me do this on the board, actually. Let me do this, too. So there's gravitational mass there in green. Boy, that was not a good m. Gravitational mass. Let me do a physics problem. I've got a scene where I drop a mass and it experiences an acceleration downward due to gravity. How much acceleration? Well, what do we have to say about acceleration? Well, we say that an acceleration comes from a net force acting on a mass. And what is the net force in this case?
Gravity.
Yeah, it's just the gravitational force. So that's just this gravitational force. And what did we just say? Like how much gravitational force acts on a mass m? The mass times g. Everybody see how I did this? This is using the gravitation force law. That was what our lab gave us, a gravitation force law. And it tells us that the gravitational force on a mass m is m times g.
So it's just G.
So it's just g. The acceleration, when something is in free fall, does not depend on
The mass.
the mass. And we had observed that last week, or maybe the week before, but we hadn't said why. Like, why is it that the bowling ball falls no faster than the marble, even though the bowling ball experiences so much more gravitational force? Everybody understand that question? There's more gravitational force pulling this object down. So why doesn't it fall down with more acceleration? Why doesn't it fall down with more acceleration? Would you talk in your neighborhood? See if you can come up with an answer with your neighbor. Why doesn't the bowling ball fall down with more acceleration? Taking attendance. We've got 7, 11, 13. And expecting 13. Why is it? Why doesn't the bowling ball fall with greater acceleration? Joe?
Because the mass isn't involved in this. It's just the gravitational force. Acceleration is the same as whatever the gravitational force is. And since they're both experiencing the same gravitational force, they'll have the same acceleration.
They both experience the same gravitational force?
Oh, well, just the mass, as you can see in that equation, isn't involved in the acceleration.
It's not in the acceleration. Yeah, so I guess like the final answer doesn't depend on mass. What happened? Why, like what happened? Why doesn't this larger gravitational mass experience more gravitational acceleration? Caleb?
The amount of gravitational force is proportional to something's mass. So like if you have a lower mass, you'll have a lower gravitational force.
Mhm.
It comes out to 10 newtons per kilogram.
What you said is that a lower mass would experience a lower gravitational force. But why doesn't it experience less gravitational acceleration? Why do they have the same acceleration? Have I understood what you said correctly?
Because it's obviously it's proportional to the amount of gravitational force. It's proportional to mass.
Yes, I agree. The amount of gravitational force is proportional to the mass. So why then doesn't the larger mass, which gives more gravitational force, give a larger acceleration when I let them go? Do you understand,
Yeah, no.
Harry?
Well, because like heavier things don't accelerate as quickly as like lighter things, and that is like reflected in it being on the bottom. That's why it's on the bottom.
Okay. It's because more massive objects are also more sluggish. Remember when we added lots of mass blocks to the horizontally moving fan cart? That made them have lower acceleration, and that shows up here. I just used the word gravitational to describe this mass. Do you know what adjective I'll use to describe that mass? This is the gravitational mass. This is the feature of an object that tells you how strongly it experiences gravitational forces. This feature of an object tells you about how hard it is to accelerate it. It is called the inertial mass. Why doesn't the larger gravitational mass give more acceleration? Because the larger mass also has more inertial mass. It's harder to accelerate the bowling ball. That's why the bowling ball doesn't experience more acceleration downward. It's because, yes, the bowling ball experiences more gravitational force, but it is also harder to accelerate a bowling ball than a marble. And that's true horizontally, too. This presence of that m in the denominator is not something having to do with gravity. It's having to do with motion. We discovered it in our lab last week with a horizontally moving fan cart. Why is it crazy? What is the surprise you're expressing? I want everybody to feel the surprise that Michael is expressing right now. What is surprising?
Why is that weird?
Yeah.
Because it's like one thing is like much more massive than the
Oh, it's a surprising.
Yeah.
It's a dramatic result that you wouldn't necessarily expect. It's true. I would like everyone to additionally feel a separate surprise. Why should these be equal? Why should these be equal? There's no good reason to that question. Physicists do not have an answer to that question. Why should these be equal? This tells you about how strongly something experiences a gravitational force. This tells you about how hard it is to accelerate something. This is its sluggishness.
But that's still a mass. That's still a mass, not a force. Because how is that embodied in mass? If you describe it as like, oh, how hard it is to push something, isn't that force?
Well, I guess I would say larger mass. This Newton's second law tells me that in order to get the same acceleration from a larger mass, you need more force.
Oh, okay.
And so mass sort of tells you about how much force you need to apply to get a certain acceleration.
Yeah.
And you need more force to accelerate the larger mass. And, sorry, this is me trying to take attendance. There's no clear reason that I can give as to why the gravitational mass of objects in our universe is the same feature as the inertial mass. But I do want to emphasize that it's not the default. In the electric force, here's what it would look like with electricity. Let's say that there's a charge Q in an electric field. Well, you don't need to know this. But again, right, like, so here's a charge. It's like an electron or something like that. And there's an electric field. There's electricity going around it. There's going to be an electric force on this electron. And here is the expression for how much force. The charge times the electric field. It's like the electric mass is not a mass. It's the charge. The feature of an object that tells you how strongly an object responds to electric fields is charge, not mass. But down here is still inertial mass. So for gravitational forces, the gravitational mass is the inertial mass. That's not the default. It's not the case for the electric force, where like the electric mass is not the same as the inertial mass. So it's not true in the electrical case that everything falls with the same acceleration. It is a huge coincidence. I guess people have some theories, about why the inertial mass might be the same as the gravitational mass, but I don't think it's well worked out or settled in physics, even among like contemporary physics researchers. But the gravitational mass equals the inertial mass, and that's why objects fall with the same acceleration. So let me try and summarize in a paragraph how that went. A couple of weeks ago, we said everything falls with the same acceleration, but we didn't talk about why. We did a lab and found that the more mass something had, the less acceleration it has for the same force. Then we did our most recent lab that says the amount of gravitational force is bigger for bigger masses. So a larger mass will experience more gravitational force, but also be more sluggish to acceleration. And that's why, regardless of mass, objects fall with the same acceleration. Harry?
So if you had the bowling ball and the marble and you like push them down with the same force, would they still go at the same?
And why don't I push them horizontally with the same force?
Okay.
I'm not sure I'm going to be able to really do it, but I'll try and really do it. Yeah, the marble experienced more acceleration for the same force. And not a very careful experiment, but I tried to push roughly equally with my two hands.
You can go ahead and scroll up a little on this
Sure.
to the gravitational mass.
Yeah, so you don't need to know about that electric business, but I do want you to know, and the Physics 1 test in May will probably ask you something about gravitational mass and inertial mass. James?
You should think about this, to like drop stuff. If you have like two objects of the same material, like a different size, they
Uh-huh.
all the same shape, but they also like bounce with the same height.
Give me that setup one more time. Two objects, same material, and
The same material, but like different sizes, different.
yeah. I don't know. I guess the question of how much energy gets lost in a bounce has to do with how something deforms when it squishes. And I'm not sure I have one thing to say that would apply to all materials about how the squishiness would happen when something squishes into, like, say, the table, when like the metal squishes a little bit and the table squishes a little bit.
Is there any material that just doesn't switch at all?
No. I mean, no. No. But there are materials that don't squish very much.
Yeah.
Or, I guess not squishing at all would give the same result as squishing and then unsquishing with no energy lost, right? Like they would both just like bounce perfectly off and rise as high as they were dropped from. Yeah. Cool. What's down here? You know, I think I'm going to save this for next time. I think I'm going to save that for next time so that we can get to a kind of lab activity. And follow me for this, Ian Colton.
If it were to not squish at all, would it like bounce forever?
Yeah, if you were to have something that didn't squish at all, you're saying that no energy would be lost as it unsquished and then squished.
Forever bouncing ball.
Yeah, I guess air resistance would take some energy out of the system, but yeah. And then there's flubber that bounces higher than you dropped it from. Well, this is a fictional material that's the subject of the Dick Van Dyke movie Flubber, and with the remake. Does anyone know who was the professor in the remake? It was Robin Williams. I think it was Dick Van Dyke originally.
Yeah, I've actually read that.
Yeah.
One of those caps that you bend.
Yeah.
Yeah. All right, everyone. I have out 6 bathroom scales. What does a bathroom scale measure? Yeah, I guess I step on it and it tells me, I don't know.
Gravitational force.
Yeah, it tells me about the gravitational. But is that right? Like I notice actually right now it says 0. It isn't telling me my weight. What does it really measure? Everybody catch that? Let me get everyone's attention on that. This bathroom scale sometimes will tell me about my weight or my mass, but not always.
Is it adjusted to gravity?
It doesn't. What's up?
Isn't it like adjusted to gravity? Like 0?
Well, I guess, but right now it reads 0. It's almost as if it doesn't actually know my weight. It's almost as if it doesn't know the force that Earth is exerting on me. What changes when I do this? What does it actually measure?
The force measure.
The force that I exert on it. What the scale actually measures is, what type of force is that I exert on it?
Gravity.
No. Earth's gravitational force on me is not a force that yeah. It measures the normal force that I'm pushing on it with. I can do that. I can pick it up here and push on it, and it can tell me how much normal force I'm exerting on it. And let me ask you, is the normal force that I exert on it a constant quantity? Like, is it possible that I could exert multiple different normal forces on it? Yeah, here I'm exerting some normal force on it, and now I'm exerting more normal force on it. So it's not that I only have the ability to exert one value of normal force on the scale. What does a bathroom scale measure?
Normal force.
The normal force that I'm exerting on it, which happens to be the normal force that it is exerting on me.
Oh, and that's why if you're really big, then you break. Because it can't match that force back up, right?
I guess that's true. Yeah. Rob?
So if it's determining your normal force on the scale, how is that relating to your like mass or your weight?
Yeah, why does a device that measures normal force help me understand my weight? Let's do this.
Well, is it normal force used
So here's the scale. Can we draw a free body diagram of me when I stand at rest on the scale?
Yeah.
Yeah, what's a free body diagram